Now we will discuss Green's reciprocation theorem, which we used in a special case to show the symmetry of the matrix of coefficients of potential, and demonstrate that the theorem is closely related to the energy of a system of conductors. The general form of Green's reciprocation theorem is the following. If phi is the potential due to a volume charge density ρ within a volume V and a surface charge density sigma on the conducting surface S bounding the volume V, while phi prime is the potential due to another charge distribution described by ρ prime and sigma prime, then the volume integral of ρ times phi prime over the volume V plus the surface integral of sigma times phi prime over the surface S, is equal to the volume integral of ρ prime times phi over the volume V plus the surface integral of sigma prime times phi over the surface S. We already demonstrated that the electric field within a cavity in a charged conductor vanishes provided no charge distributed over an insulator or charged conducting material insulated from the conductor is placed into the cavity. Since the volume charge densities ρ and ρ prime in the theorem represent such distributions of charges within the volume V enclosed by the charged conductive surface S, we can talk about a non-zero electric field within the volume V described by the non-constant potentials phi and phi prime. In order to prove the theorem, we apply Green's second identity stating that the volume integral of the difference between phi times the Laplacian of phi prime and phi prime times the Laplacian of phi over the volume V, is equal to the surface integral of the difference between phi times the directional derivative of phi prime in the direction of the outward pointing surface normal n to the surface S of the volume V, and phi prime times the directional derivative of phi in the direction of the surface normal n. Here the normal n points away from the volume V that is into the conductor, since the volume V is the non-conducting region bounded by the conducting surface or surfaces S. The Laplacian of the potential phi in the volume integral is equal to the divergence of the gradient of the potential, where the negative gradient of the potential is equal to the electric field strength E of the electrostatic field described by the potential phi. Then we can use Gauss' law stating that the divergence of the electric field E is equal to the electric charge density ρ producing the field over the vacuum permittivity epsilon naught. As a result, we have Poisson's equation stating that the Laplacian of the electric potential phi is equal to minus the electric charge density ρ over epsilon naught. Similarly, we can write that the Laplacian of the potential phi prime is equal to minus the electric charge density ρ prime over epsilon naught. If we substitute the two Poisson's equations into the Laplacians in the left-hand side of the identity and multiply the result by epsilon naught, we can write that minus the volume integral of the difference between phi times ρ prime and phi prime times ρ over the volume V, is equal to the surface integral of the difference between epsilon naught times phi times the directional derivative of phi prime, and epsilon naught times phi prime times the directional derivative of phi over the surface S. We already demonstrated that the electric field is perpendicular to the surface of a charged conductor and its magnitude is given by the ratio of the surface charge density sigma to epsilon naught. Since the surface of a conductor is an equipotential surface, the electric field E given by the negative gradient of the potential phi is equal to the directional derivative of the potential in the direction of the outward pointing surface normal n of the conductor, and we can express the surface charge density sigma as minus epsilon naught times the directional derivative of the potential phi in the direction of the surface normal n over the surface S. Here the normal n is directed outward from the volume of the conductor, while the normal n in Green's second identity points inward. If we reverse the direction of the normal, then sigma is equal to the directional derivative of phi in the direction of the surface normal n pointing inward the volume of the conductor, and we can write the same equation for sigma prime and phi prime. By substituting these two expressions into Green's second identity, we obtain the equation stating that minus the volume integral of the difference between phi times ρ prime and phi prime times ρ over the volume V, is equal to the surface integral of the difference between phi times sigma prime and phi prime times sigma over the surface S. Now we can expand the brackets in the integrals and shuffle the second terms in both sides, which gives Green's reciprocation theorem. After having proven the theorem, we explain how it is related to the potential energy of a system of charged conductors. First, we note that the electrostatic potential energy U of a volume charge distribution ρ producing the electrostatic potential phi, is given by 1 over 2 times the volume integral of the product of the electric charge density ρ and the potential phi over the volume V enclosing the non-vanishing region of the charge distribution. For an electric charge distribution sigma over a surface S, the volume integral providing the potential energy U can be reduced to the surface integral of sigma times phi over the surface S. By taking a look on the volume and surface integrals in Green's reciprocation theorem and comparing them with the two integrals of the electrostatic potential energy of a charged system, we can interpret the reciprocation theorem as follows. If the charge densities ρ and sigma were at rest in the potential phi prime, then their total potential energy would be the same as that of the charge densities ρ prime and sigma prime held at rest in the potential phi. In order to illustrate this statement, let us derive the version of reciprocation theorem for systems of point charges from the definition of the electrostatic energy of such systems. We already demonstrated that the potential energy U of a system of point charges Q1, Q2, ellipsis, Qn at the positions R1, R2, ellipsis Rn is equal to 1 over 2 times the sum of Qi times phi I from I equals 1 to n, where the potentials phi I are given by the sum of 1 over 4 pi times epsilon naught, times the charge Qi over the distance R sub ij from j equals 1 to n excluding I. Here R sub ij denotes the distance between the charges Qi and Qj. We also consider another system of point charges Q'I at the same positions producing the potentials phi prime I from I equals 1 to n, where Qi is replaced by Q'I in the formulae of the potentials. Now we start with the computation of the product of the charge Q1 and the potential phi prime 1. By inserting the explicit expression of the potential and expanding the sum in it, we obtain 0 for j equals 1, plus 1 over 4 pi epsilon naught, times Q1 times Q prime 2 over R sub 1 2. Plus 1 over 4 pi epsilon naught, times Q1 times Q prime 3 over R sub 1 3, plus ellipsis, plus 1 over 4 pi epsilon naught, times Q1 times Q prime n over R sub 1 n. We also expand the product of the charge Q2 and the potential phi prime 2, which gives another sum with the vanishing second term in the right-hand side. If we multiply the charge Q3 by the potential phi prime 3, we obtain a third sum where the third term is 0 in the right-hand side. We can continue this procedure till the product of the charge Qn and the potential phi n, which gives the last sum with the vanishing last term. Now we have an equations where can add the terms in each column separately. If we add the left-hand side of these equations, then we obtain the sum of Qi times phi prime I from I equals 1 to n. The sum of the terms forming the first column in the right-hand side gives Q prime 1 times the sum of 1 over 4 pi times epsilon naught, times Qj over R sub 1 j from j equals 1 to n excluding 1. By summing up the terms in the second column, we have Q prime 2 times the sum of 1 over 4 pi times epsilon naught, times Qj over R sub 2j from j equals 1 to n excluding 2. Similarly, if we add the terms in the third column, we obtain Q prime 3 times the sum of 1 over 4 pi times epsilon naught, times Qj over R sub 3j from j equals 1 to n excluding 3. We can continue this procedure up to the last column, where the sum is equal to Q prime n times the sum of 1 over 4 pi times epsilon naught, times Qj over R sub nj from j equals 1 to n excluding n. Now we can add all the sums obtained in the right-hand side, which gives the sum of Q prime I times phi I from I equals 1 to n. As a result, we have a special case of Green's reciprocation theorem for the systems of electric charges Qi and Q prime I at the same positions producing the potentials phi I and phi prime I from I equals 1 to n, which states that the sum of Qi times phi prime I from I equals 1 to n, is equal to the sum of Q prime I times phi I from I equals 1 to n. If we compare this result with the potential energy for a system of charges, then we can immediately give the same interpretation of the special case of the theorem as in the general case. That is, if the system of charges Qi were at rest in the potential phi prime I, then their total energy would be the same as that of the system of charges Q prime I held at rest in the potential phi I, where I runs from 1 to n. We use this special form of the theorem to prove that the matrix of coefficients of potential is symmetric. However, we need to clarify how to apply the theorem proven for a space enclosed by a conducting surface to a set of conductors without any boundary surface around them. When we studied the capacitance of a system of conductors, we considered an arbitrary arrangement of charged conductors or electrodes, and determined the relationship between their potentials and the charges distributed over their surfaces. Although the Earth was also the part of the system as an electrode 0 of 0 potential, the conductors 1, 2 and so on were not enclosed by another conducting surface in the general case. However, even in the general case, the finite amount of charges Q1, Q2 and so on distributed over the surfaces of the conductors 1, 2 and so on are localized in space, and the electric field produced by these charges vanishes at infinity. Therefore, any imaginary equipotential surface S0 of 0 charge and 0 potential at infinity joined with the Earth or the electrode 0 can be considered as an uncharged conducting surface that encloses the system of charged conductors. The union S of the conductive surface S0 and the boundary surfaces of the electrodes 1, 2, and so on denoted by S1, S2 and so on forms a boundary of the volume V enclosing the region of the system of electrodes but excluding the electrodes themselves. As a result, this problem is equivalent to the one described by Green's reciprocation theorem, where the surface charge density sigma describing the distribution of charge over the surface S is given by the different surface charge densities sigma 1, sigma 2 and so on over the patches S1, S2 and so on of the boundary S. If there are no space charges in some dielectric medium between the conductors within the volume V, then the volume charge density ρ vanishes. These statements hold for the primed versions of sigma and ρ as well. For vanishing ρ and ρ', the reciprocation theorem reduces to the surface integrals over the boundary surface S. We can break up the surface S into the patches S0, S1, S2 and so on in the surface integrals, where each patch represents an equipotential surface. Then the constant potentials phi and phi prime can be factored out from the surface integrals over the patches, leaving only the surface charge densities sigma and sigma prime in the integrals. Since the integrals give the total charge Qi over the patch Si, that is the surface of the conductor I, we regain the reciprocation theorem. For the total charges Q1, Q2, ellipsis Qn distributed over the surfaces of the conductors 1, 2, ellipsis, n producing the potentials phi 1, phi 2, ellipsis, phi n of the conductors, the sum of Qi times phi prime I from I equals 1 to n is given by the sum of Q prime I times phi I from I equals 1 to n. Here the charges Q prime I distributed over the surface of the conductors I produce the potentials phi prime I from I equals 1 to n. This is the form of the theorem applied to prove that the matrix of coefficients of potential, and therefore the capacitance matrix of the system of conductors is symmetric. This form also follows from the expression obtained for a system of point charges if we assume that the point charges are distributed over the surfaces of conductors. Since these surfaces are equipotential surfaces, the sums in both the sides of the expression can be written as the sums of the constant potential of a given conductor times the sum of the point charges on the surface of that conductor, that is the total charge of the conductor. An immediate consequence of the theorem is the following. If the charge Q1 is equal to the charge Q'2 while all the other charges Qi and Qi' vanish, then the theorem can be reduced to the equation stating that the potential phi'1 is equal to the potential phi2. Let Q denote the equal charges Q1 and Q'2, and consider a situation where we charge only one electrode in the system by bringing the charge Q to the electrode 1 while all the other conductors remain uncharged. Then the electric field produced by this charge will induce charges on the surfaces of the uncharged conductors, which raises their electric potential. If we bring the charge Q to the electrode 2 while all the other conductors are uncharged, then this charge also raises the potential of the uncharged conductors. The consequence of the theorem states that the potential to which the uncharged conductor 1 is raised by putting the charge Q on the conductor 2 is the same as that to the conductor 2, when uncharged, will be raised by putting the charge Q on the conductor 1. Another consequence of the theorem is related to the superposition of electric fields. If we add the sum of Qi times phi I to the equation in the theorem, then we obtain an equation stating that the sum of Qi times the sum of phi prime I and phi I is equal to the sum of Q prime I and Q prime I times phi I. By comparing the result with the equation in the theorem, we can see that if the charges Q1, Q2, ellipsis, Qn produce the potentials phi 1, phi 2, ellipsis, phi n, then the charges Q1 plus Q'1, Q2 plus Q'2, ellipsis, Qn plus Q'n give the potentials phi 1 plus phi prime 1, phi 2 plus phi prime 2, ellipsis, phi n plus phi prime n. This consequence shows that many problems in electrostatic can be solved by superimposing of the solutions of known problems. We have already determined the energy of a system of electric charges which is applied when we ask how much energy a given system of conductors has. We obtain this energy by calculating the work required to produce a state in which the conductors have given charges and potentials. As a result, the electric energy of a system could be expressed in the terms of charges and potentials. Now we express the electric energy of a system of conductors in the terms of capacitances and potentials or charges, and we show that it can be done by applying the quantities describing the electric field. We determine the energy of a charged capacitor given by the work required to bring charge to its plates. If the conductors A and B are the plates of the capacitor of capacitance C, then the energy of the capacitor can be calculated as follows. At a given instance of time t, let Q' and minus Q' be the charges on the plates A and B, respectively. Then the voltage V between the conductors is equal to the charge Q' over the capacitance C, where Q' and therefore the voltage V depends on the time t. If we bring an infinitesimal positive charge dQ' from the plate B to the plate A, then the work dW done against the electrostatic force between the plates is given by the voltage V, that is the difference of the potential between the two plates, times dQ'. This work can be expressed as Q' over C times dQ'. The work W required to bring the charge Q to the initially uncharged capacitor is the sum of such infinitesimal works, that is the integral of dW, or the integral of Q' divided by C from 0 to Q with respect to Q'. Since the capacitance C is constant, the primitive function of the integral is equal to the square of Q' over 2 times C, and the work W is given by 1 over 2 times the square of the charge Q divided by the capacitance C. If the capacitor is gradually charged, in each step a given amount charge is brought to its plates producing an electric field between them, but no other change occurs. As a result, we can assume that the work required to charge the capacitor is completely converted into the energy of the charge Q. Then the energy U of a capacitor storing the charge Q is equal to 1 over 2 times the ratio of the charge Q squared to the capacitance C of the capacitor, or 1 over 2 times the capacitance C times the square of the voltage V between the plates of the capacitor. This result holds for any capacitor independently of its structure. It is also valid for a single conductor provided the voltage V is equal to the electric potential of the conductor with respect to a point at infinity. The inverse process of the gradual charging of a capacitor is its gradual discharging, where the capacitor can do work on any physical system residing its electric field. The experiment shown in the figure illustrates how work is done during the discharge of a capacitor. A small metal sphere suspended from a string made of silk will attain positive charge when it is brought into contact with the plate A of the capacitor. As a result, the ball is repelled from the plate A and attracted to the plate B due to the electrostatic forces between like and opposite charges. When the ball gets into contact with the plate B, it loses its positive charge and attains -1. Then the electrostatic forces drive the ball from the plate B to the plate A, where it reduces the positive charge of the plate A, and so on. The gradual decrease in the charge of the capacitor or in the voltage between its plates can be measured by an electroscope connected to the plate A of the capacitor. In order to provide the general expression for the energy density of an electrostatic field, we determine the energy of the electrostatic field and its density between the plates of a capacitor. We have seen that the energy U of such a field is given by 1 over 2 times the capacitance C of the capacitor, times the square of the voltage V sub C between its plates. For parallel plate capacitors producing a uniform electric field E between their plates, the voltage V sub C defined by the difference in the potential phi between the plates is equal to the magnitude of the electric field E times the distance d between the plates. We also demonstrated that the capacitance C of a parallel plate capacitor is given by the dielectric constant of vacuum epsilon naught, times the area A of the plates of the capacitor over the distance d between the plates. If we substitute these equations into the expression of the energy U, then we obtain 1 over 2 times epsilon naught times the square of the magnitude of the electric field E, times the area A times the distance d. Here the volume V between the plates is given by the area A of the plates times the distance d between them, and the energy U of the electric field is equal to 1 over 2 times epsilon naught, times the square of the magnitude of the electric field E times the volume V. We can interpret this result as the fact that the energy U is not distributed over the plates of the capacitor but it is stored in the volume V between the plates, where the electrostatic force field is produced. Since this field is uniform for parallel plate capacitors, the energy per unit volume, that is the energy density denoted by lowercase u, is equal to 1 over the vacuum permittivity epsilon naught, times the square of the magnitude of the electric field strength E. Although we derived this result for parallel plate capacitors, it holds in the general case as well. In other words, the energy density of an electrostatic field at any point of the field is directly proportional to the square of the electric field strength at the given point. For example, the magnitude of the electric field E due to a charged sphere at the distance r from its center is given by 1 over 4 pi times epsilon naught, times the total charge q of the sphere divided by the distance r squared. Then the energy density lowercase u of the electrostatic field due to the charged sphere is equal to 1 over 32 pi squared times epsilon naught squared, times q squared over the distance r raised to 4. That is, the energy density of a charged sphere is inversely proportional to the fourth power of the distance from its center. The same relationship holds for the electric field due to a point charge as well. For non-uniform electric fields, the general expression of the energy density lowercase u is defined by the derivative of the energy U with respect to the volume V. Then the infinitesimal amount of energy du within the infinitesimal volume element dV is equal to the energy density lowercase u times the volume element dV. By inserting the result obtained for the energy density into this equation, we can write du as 1 over 2 times epsilon naught times E squared times dV. The total energy of the electrostatic field is equal to the integral of the infinitesimal quantity of du, or the volume integral of the energy density lowercase u. And as the formula shows, the general expression of the energy U of a non-uniform electrostatic field is given by 1 over 2 times the vacuum permittivity epsilon naught, times the volume integral of the square of the electrostatic field strength E. We note that this formula describes the energy of a capacitor in the terms of electric field strength produced in the space between the plates of the capacitor, as opposed to the expression written in the terms of the charge distributed over the plates, the capacitance of the capacitor or the difference in the potential between the plates. From the viewpoint of electrostatics, we have to ask the question where energy is localized, or what is the medium of energy? Either electric charge or electrostatic field? In electrostatics, where we study static electric fields due to charges at rest, this question cannot be answered, since static electric fields and the charges at rest producing them do not exist in separation from each other. It is however not the case for time-evolving electric fields, which can exist independently from the charges producing them and propagate in the form of electromagnetic waves. Experiments already demonstrated that electromagnetic waves can transport energy, and the medium of energy is the electromagnetic field. Now we determine the energy of a system of charged conductors based on the general formula expressing the energy of an electrostatic field in the terms of the field variables, and derive another formula depending on the capacitances of the conductors in the system. We consider a system of charged conductors 1, 2 and so on having the charges Q1, Q2 and so on, where the system is localized and the electric field due to the charges vanishes at infinity. Then the electrostatic energy U of the system is given by 1 over 2 times epsilon naught, times the volume integral of the square of the electric field strength E. Here E squared is simply equal to the dot product of the electric field strength E, and we can write any of the factors in the dot product as the negative gradient of the electric potential phi. If we use the product rule for derivatives, then we can split the volume integral into the integral of the divergence of the product of phi and E, and the integral of the divergence of E times phi. Since there are no space charges in the volume over which these expressions are integrated, that is the volume charge density ρ is 0, Gauss's law tells us that the electric field is divergence-free and the second integral vanishes. In the first term we can apply Gauss's theorem, and write the volume integral of the divergence of phi times E as the surface integral of phi times E over the surface boundary S of the volume V enclosing the electrostatic field. The dot product of phi times E and the surface element S in the surface integral indicates that only the projection of the electric field onto the surface normal gives a contribution to the integral. As the figure shows, the volume V enclosing the localized electric field due to the system of charged conductors has the boundary S, that is the union of the surface S0 and the boundaries S1, S2 and so on of the electrodes 1, 2 and so on. Here the surface S0 is a surface of zero potential, that is the combination of the Earth considered as the electrode 0 and an imaginary surface at infinity where the potential of the localized electric field vanishes. Then we can split the surface integral into the sum of integrals over the charged boundaries of the n conductors in the system, where we omitted the integral over the surface S0 of zero potential. Since the electric field E is always perpendicular to the boundary of a conductor in its vicinity, we use the component of E that is normal to the surface in the integral. The change in the sign of the integral indicates that E sub n points outward from the surfaces of the conductors, which is opposite to the outward normal to the boundary of the volume V of the integration. We can also factor out the constant potential phi from the integrals over the boundaries of the conductors, which are equipotential surfaces. The normal component of the electric field is just equal to the negative gradient of the potential in the normal direction, that is the directional derivative of phi in the direction of the surface normal n. The positive sign of the directional derivative is the consequence of the fact that the normal n points outward from the volume V and inward to the conductor, that is in the direction of the increasing electric potential outside the conductor. We already saw that epsilon naught times the directional derivative of the potential in the normal direction n is equal to the surface charge density sigma over the surface of the conductor. Again, the missing negative sign in the front of the derivative indicates that the normal used here points outward from the volume V and inward to the conductor. By inserting this expression into the sum of integrals, we obtain the surface integrals of the surface charge density sigma I of the charge distributed over the boundary Si of the conductor I for I running from 1 to n. These surface integrals then give the total charge distributed over the surface of each conductor, and the energy of the electrostatic field due to the charges distributed over the surfaces of conductors, is given by 1 over 2 times the sum of the potential phi I of the conductor I, times the charge Qi of the conductor I from I equals 1 to n. We already established that the potentials phi I can be expressed as functions of coefficients of potential and charge, or in the inverse problem the charges Qi can be written as functions of partial capacitances and potentials. As a result, the energy U has a quadratic form, that is U is equal to 1 over 2 times the sum of the coefficient of potential A sub ij, times the charge qi, times the charge qj from I and j equal 1 to n, or 1 over 2 times the sum of the partial capacitance given by the inverse of A sub ij, times the potential phi I, times the potential phi j from I and j equal 1 to n. When the electrostatic energy is expressed as a quadratic form of the potentials, partial capacitances are used to define the elements of the Maxwell capacitance matrix. Then the electrostatic energy U of n charged conductors is given by 1 over 2 times the sum of the element ij of the Maxwell capacitance matrix Cm, times the potential phi I of the conductor I, times the potential phi j of the conductor j from I and j equal 1 to n. We already introduced the capacitance matrix of a system of conductors and express the partial capacitances of the system as functions of the elements of the capacitance matrix. If we replace the partial capacitances by the elements of the Maxwell capacitance matrix, then we can write the diagonal elements of the Maxwell capacitance matrix Cm for the index I as the sum of the elements ij of the capacitance matrix C from j equals 1 to n. We also mentioned that the elements of the capacitance matrix are positive. Hence the diagonal elements of the Maxwell capacitance matrix must be positive. The off-diagonal elements of the Maxwell capacitance matrix Cm are equal to minus the corresponding elements of the capacitance matrix C. Since the later ones are positive, the off-diagonal elements of the Maxwell capacitance matrix are negative. In fact, these properties follow from the positivity of electrostatic energy. We can see that the energy U given by the volume integral of the square of the magnitude of the electric field is positive definite, and the quadratic forms of the electrostatic energy must be positive definite as well. Then the signs of the capacitance matrices can be justified by solving Laplace's equation over the volume enclosing the field and determine its positivity in the whole space. A less formal justification can be given by supposing that all conductors except the conductor I are grounded. In the figure, the conductor I is the first electrode. Then the electric charges of all conductors are proportional to the potential of the conductor I, where the constant of proportionality for the conductor J is the element ij of the Maxwell capacitance matrix. Since the potential and the electric charge of the conductor I have the same sign, the diagonal elements of the Maxwell capacitance matrix must be positive, which holds for an arbitrary index I. In presence of the isolated conductor I with charge, there will appear induced charges at surfaces of all remaining grounded conductors such that their sign will be opposed to the charge of the conductor I. In other words, the sign of induced charge is opposed to the sign of inducing potential. It means that the off-diagonal elements of the Maxwell capacitance matrix must be negative, that is, the off-diagonal elements of the capacitance matrix must be positive.